just going to pull up my slide deck. Are we all good? Everyone sees the slides? Awesome. Yeah, as I mentioned, thanks so much for joining us today. Really excited to be here to talk a little bit about what I get to do in my day-to-day and what my team does in our day-to-day, which is, of course, manage machine learning products. And we do that from the very beginning stages of ideation all the way through to production and what happens after production for us. And why I thought this was a particularly interesting topic to speak on is the fact that machine learning products are inherently different than traditional software products. And I'll talk a little bit about that in my presentation today. And obviously, as product managers, we have a responsibility to deliver value to our end user, and we are responsible for the success of that product. And so it's really important that we understand those challenges, those differences, and we also understand how to manage them. And so today what I'm going to do is give you a super high level introduction to machine learning. I'm sure many of you have heard that term. Some of you might know a ton about it already. Not going to spend too much time there. I'm also going to introduce what the difference is between a machine learning product versus a traditional software product. And then I'm going to spend the majority of my time really walking through how we at Borealis deal with some of these challenges and the uncertainty associated with machine learning as we go through our product lifecycle. And before I jump into the meat of my presentation, I think it is helpful just to set a little bit of context and give you a view of where I'm speaking from. And so I want to introduce you to my organization. It's Borealis AI. We're actually part of RBC, but we're at arm's length, meaning we have a fair bit of autonomy in terms of how we work. We look quite different from the rest of the bank. And we're actually a research institute, and we really work at the intersection of three key pillars. Those pillars being research or state-of-the-art algorithms, machine learning, and of course, financial services and banking. And I'm going to leave that research bit off the table. That actually brings in a whole other level of complexity to the work that we do. But really just going to focus my talk in on machine learning and what makes that different. So not going to go through all of these details, just want to give you a sense of the type of work we do. While we are a research institute, we're actually very heavily product focused. So we have about 10 product teams, and those product teams service various different lines of business across the enterprise, from capital markets to personal and commercial banking to risk management. And of course, to do the work that we do at Borealis, we need specialized resources to do that. And I mean that in a couple of different ways. One is, of course, our people, and I'll talk a little bit about that on the next slide. But the other piece is really our infrastructure and our tooling that we need to do the work that we do. And we are very, very lucky at Borealis that we have a sizable GPU cluster. We have access to about 274 GPUs. This is split across our development and prod environments. And we use this day in and day out on our teams to be able to build the models that we build for our stakeholders. Of course, on top of this infrastructure, we also have specialized tooling. I'll talk a teeny bit about tooling that's used for machine learning, but largely I'm going to stay away from that topic. But that really covers everything from experiment tracking all the way to model serving when we push things to production. Right now, our org has about 7 products live in prod that are actively being used by RBC. So in terms of our team, every single product team that we have at Borealis has 4 functional teams that it's comprised of. Research, of course, is kind of like our data science team. They're a little bit different, obviously, as they are researchers, but they're really responsible for developing all of our algorithms. So when we're looking to build out a candidate model for production, that really starts with our research team. Once we have a model, passes that over to our engineering team, who of course takes that model and builds it into software, and then it also deals with everything in terms of production and integration. As part of our engineering team, of course, we also have an infrastructure team and a tooling team that make sure that they're supporting our work throughout our development cycle. My team in particular is comprised of 2 functional components. One of those components is our business development lead. And you can think of this somewhat like a traditional business development team in a tech firm. So this would be kind of salesy. That being said, because our exclusively we build for RBC, obviously it's a little bit different. And so really on my BD team, we have deep financial knowledge. So experts in the banking industry across various different areas. And that's really important for us in terms of being able to act as effective translators. And so what that means is translating our business needs to technical speak, translating our technical speak to business terms, making sure that we're doing that really effectively, understanding our lines of business, understanding where the big high value pain points are and where we should be focusing our time and our capabilities. And of course, last but not least on my team are the product managers. You guys don't really need an introduction to what product managers do, but really they're the glue that pulls it all together. They set our short-term roadmaps and our long-term visions, and really make sure that everything is moving smoothly forward. So now on to the exciting stuff, which is the machine learning bits. And to start that off, I wanted to give a little bit of an introduction to what machine learning is, but I thought I would take first a step back and talk about artificial intelligence, AI. I think there's so much hype about AI. I think people have widely different opinions of what it is and what it isn't. On one end of the spectrum, you have people that are kind of thinking Terminator-esque, super intelligent robots that can walk around. Luckily, we're very, very far from that type of highly generalized AI. And really, when we think about AI in that context, one of the things that we're thinking about is this ability to learn a task in one particular domain and perfectly generalize that to another domain. And so if you've ever been around small children, you'll see them doing this quite effectively, where they might learn something in one context and apply that learning in another context. And sometimes they get it right, sometimes they don't. But we're quite far from that type of kind of generalized learning. And so where are we today? One of the main ways that we can drive forward with artificial intelligence is, of course, machine learning. And the way that I think about machine learning is really, it's a toolbox of methods that can be applied to a very diverse set of problems. And it really allows computers to learn about a particular task without being explicitly programmed. And I'm going to dig into that piece in a couple of slides. So just hold that thought in your mind. In terms of how we talk about machine learning, one of the main ways that we classify a machine learning algorithm is by the data that it ingests. So for those of you who are familiar with it, you've probably heard the term supervised learning, unsupervised learning, reinforcement learning, giving you a really quick crash course in what those mean. Super simple concept. So say I want to build an algorithm that's going to classify pictures, and I have a pile of pictures. Some of those pictures are of cats. Some of those pictures are of dogs. If I were to build a supervised learning algorithm, what I would need to do is provide my algo with labeled data. And so that means beside all of those pictures, I will have already said, well, that's a picture of a cat. That's a picture of a dog. We could feed all of this information into the computer. And so when we provided a new picture that doesn't have a label, it can take all of its learnings based on the information I've shared about what cats and dogs look like, and it can give me a classification on that picture. That's supervised learning. So we are supervising the learning of that algorithm. Unsupervised learning, we basically take away those labels. So we'll make inferences based off of the information that it has available. Maybe it's the pointiness of the ears or the color, and it will split that into the number of groups that we specify. Reinforcement learning is kind of a totally different beast. The easiest way to think about reinforcement learning is if I were to build an algorithm to play chess, I would use a reinforcement learning algorithm. It's a way to optimize an end state. Of course, winning chess is our ultimate goal. And it optimizes that through various decisions that we'll make along the way. Another term that's very commonly used in the ML space, of course, is deep learning. A subset of what we do at Borealis is deep learning. Not everything that we do at Borealis is deep learning. Generally, what deep learning means is it's very large models, highly complex, and lots of data. We're talking terabytes of data to build out these algorithms. And there's a lot of very interesting applications of deep learning that have come out over the last couple of years. If you want some reading and some things to look into after this talk, I do encourage you to take a look at GPT-3. It's a deep learning model that has gotten a lot of press in recent years, and it can do some pretty incredible things. So now bringing this back to our talk and product management, really the key question is what makes machine learning systems different? So I've split this into two contexts: software 1.0, traditional software, and software 2.0, machine learning based software. Software 1.0 really consists of explicit instructions, right? So every time we are writing a piece of code or writing a line of code, that line of code has some explicit instruction. And what that means is there's very little uncertainty in terms of how that code at the end of the day is going to behave. We've made very specific rules in terms of what we expect. And of course, with any software development, any technical project, there are uncertainties, there are risks, But we have a pretty good idea that if we have a set of rules and we program them in, we know how that program is going to behave. Machine learning, on the other end, provides us a lot more flexibility in terms of the types of problems that we can automate. So a much larger set of things that we can do. And at the beginning stages, we approach it largely like we would traditional software. So we ask ourselves the question, what is the desired goal or outcome? And so a couple of examples could be that we want to predict cash flow at time t.1. It could also be that we want to win a game of chess. In order to do that task, what we're going to do next is provide a rough skeleton of code. And generally that rough skeleton is some form of model architecture. So it could be a neural network architecture. And that neural network architecture has some gaps in it. There's some things that we have to figure out to complete the code. And we complete the code via data, and of course, using our wonderful GPU cluster at Borealis to run some experiments. And what that allows us to do is specify all of the parameters and the hyperparameters within that model architecture. And what we're really trying to get at is a program that does that task that we want to do. But remember, we're inferring based off of history because we're using historical data. And the process that we're using is a form of optimization, and there's some stochasticity to that. And what that means is, with all of that flexibility that we get from machine learning systems also comes a huge amount of uncertainty. And as product managers, we have to figure out how to pinpoint that uncertainty and how to manage that uncertainty. And so really that's going to be the central point of my talk, is around how we manage uncertainty associated with machine learning throughout development cycles. And of course, in order to do this, it's really helpful to have a set of tools that help you do that. And one of the tools that we lean on a lot at Borealis is our product lifecycle. It's a common process and a common language we can use to really understand where we are with a particular project. All of our teams understand what the expected inputs are to every phase of the product lifecycle, as well as the expected outputs. And we also understand the key characteristics of our product lifecycle. And this is something that we have developed internally. Obviously, this is a concept that is borrowed from product management, but we've made it our own. And a couple of important things to note about our product lifecycle are: one, it is very flexible. This is a process that is, or a tool, I should say, that is meant to help out our teams in navigating some of the uncertainty that exists while we're developing machine learning products. It's very iterative, and you'll hear me use this word over and over again as I walk through my talk. There is iteration in every single phase. A great example of this would be as we're developing out models, we do a ton of iteration. It's experiment after experiment. We bring that back to the business, we go back to the table, and that process can often last quite a lengthy period of time. Our product lifecycle is also circular, and that means that we could end up in production and we could learn a whole bunch of new data, have access to a whole bunch of new data from our end users. And with that new data, we may head right back to discovery and think about what's the next feature we're going to build. We could also learn that our model isn't quite as good as we thought it was, and that might shoot us right back to model development. And so we're always kind of bouncing back and forth, with reason, of course, throughout our product lifecycle. But we really use this to make sure that we're all on the same page in terms of expectations throughout. So to help with my talk today, I'm going to use our product lifecycle as kind of a guide. And throughout each of these phases, I'm basically going to bring up big questions that our product managers have to be thinking about throughout the cycle. And I'm going to start with discovery. And of course, as product manager, you guys have all been here, done that. And a lot of the tools that exist for navigating discovery from traditional product management definitely apply here, and we use many of them. Discovery for us is really about identifying the right problem, understanding the problem space, framing the business problem, making sure we pinpoint that desired outcome, right? So that probably doesn't look any different from what you guys would deal with in your day-to-day. So I'm really going to spend time highlighting what makes us different. And the first, foremost, biggest question, and you will see this a couple of times throughout my talk, is asking yourself the question, is machine learning the right solution? Right? Of course, we exclusively do machine learning at Borealis, and so we really need to make sure that anything that's coming in, anything that we're agreeing to take on is in fact a machine learning problem. Obviously, not all product teams have this type of constraint, but it's what we work within, and so is really a key consideration for us in discovery. A couple of things that might help you answer that question. One, a big one, of course, is data. Is it accessible? And I kid you not, I've definitely been in meetings with business stakeholders who have had what seems to be on paper a really great problem. When we ask about the data, they say it's in that filing cabinet over there. Unfortunately, my team can't do anything with that. If the data isn't digitized and easily accessible, it's really challenging for us to build a model on top of that. Of course, with machine learning, we also need a decent quantity of data, and it goes without saying almost that you need quality data. I'm sure many of you have heard garbage in, garbage out. If we're basing our models on historical data, we want to make sure that data is as best of quality as possible. Another question we ask ourselves is about generalizability and complexity. If you can distill your task down into 5 rules, you probably don't need a machine learning system, right? We're really looking for those cases where there are way too many instances to program manually, or there's really complex, highly nonlinear relationships. A couple of examples of this could be coming back to cash flow forecasting. We can't possibly do cash flow forecastings for every single RBC client by manually coding that in, right? A model is a great way to do that, and machine learning is a great way to do that. In terms of nonlinear relationships, if we wanted to predict the stock market, it's a very complex problem. It could potentially be a good machine learning problem. You also have to consider things like error tolerance. Remember, with rules-based approaches, we know exactly what we're going to get out of that. If there is a very, very low error tolerance, you may not want to use a machine learning system. Machine learning is stochastic. It is definitely going to get some things wrong. And last but not least, and this one is often overlooked, I would say, is the cost of machine learning. Oftentimes we consider development cost of machine learning, but we forget about the production cost of machine learning. Generally in production, we need specialized tooling to support that. We often need access to GPUs. Machine learning can be exceptionally expensive. You really want to make sure that the problem that you're using, or the problem that you're focusing in on, if you're building a machine learning solution, that the business impact far, far outweighs the cost. And the last point I'm going to make is around building trust. And of course, this is something as product managers we always have to do, and this applies to anything. But I definitely think it's key when you have differences in terms of where people are coming to the table, right? So we work with business partners. They are deep experts in their business domain. They don't know very much about machine learning. And so a lot of education has to go back and forth when we start off an engagement. And a part of this is really developing that culture of iteration, letting them know that our timelines, we could end up spending 6 months exploring something and come to the conclusion that it makes no sense at all. And they have to be comfortable with that. And last but not least, machine learning takes time. And one of the things that we try to do is find short-term deliverables. And so maybe that is a linear baseline model that we'll put into production, as opposed to waiting to get that perfect machine learning solution, which could take 6 months. It could take a year or 2 years even. Which brings me to feasibility. So we feel like we have a good machine learning problem. And now the whole purpose of feasibility is testing that hypothesis. Basically confirming, is this actually a good machine learning problem? We're going to start digging into the data. We're going to start doing some explorations. And we're going to do some rapid experimentation and baselining. And this basically gives us a sense of, how good is the data and what can we get out of it? Based on the models that we've been able to pull together really quickly, do we have confidence that if we keep on this track for a little bit longer, we're actually going to be able to provide business value in the end of the day? And one of the key tasks for a PM during this time is to get clear performance metrics and requirements. And this is actually quite difficult. Oftentimes, our business partners have a really clear sense of what they're looking for, but they don't know how to translate that into technical requirements. So that could be accuracy, it could be some form of performance metric. And one of the big jobs a PM has to do is navigate that, figure out what it means for 99% accuracy for user experience, for example. And that's where a lot of my PMs spend a lot of their time during feasibility. Again, it comes back to confirming business impact. So thinking about the cost of errors. If you have a need for almost a perfect solution, and 99.9% accuracy might not be a machine learning solution. And last but not least, coming back to this idea of iteration. It's all about reframing, potentially downscoping. And so what we might find after doing a series of experiments is we couldn't do the initial task we defined, but in that exploration of data, we actually found this other really interesting task that we think is going to have big business impact. Or it could be, say we're dealing with a large population of clients that we have really great data on one set of clients, but we don't have very good data on the other. And maybe that means that we have to downscope our solution. And so, of course, as PMs, we would go back to our business partner and ask if this actually makes sense from a business perspective to move forward. So walking out of feasibility, of course, we have some sense that this is a machine learning problem, onto design and requirements. And I'm not going to spend too much time here. This actually looks very, very similar to traditional product management when it gets to this point. It's really about, of course, understanding your user's needs, and thinking about what that might look like from an experience perspective. And really, all of our focus here lies on doing user research, user experimentation, building wireframes, et cetera, and getting a little bit deeper into that question of what does it feel like when a system gets something wrong? What is the tolerance level of the end user when they're using a machine learning system? And we have to think about a couple of different things here. One is there's certain contexts where if we get it wrong, it's a really, really bad outcome, right? And so if we think about Netflix, actually Netflix on the back end is wholly powered by machine learning. Basically everything that you see on Netflix has been decided by an algorithm in terms of the ordering that you see, the pictures that you see, the text that you see. Everything is chosen based off of your historical behavior with the platform. Now, if Netflix gets something wrong, right, you might waste an hour on a really bad TV show or an hour and a half on a really bad movie. Risk of that is not so great, right? So they can take a little bit of leniency in terms of what their model accuracy is and what that means for user experience. Now, as we work with RBC, say, for example, we were building out a cash flow algorithm, and we actually do have one live if you want to check it out. But if we were building a cash flow algorithm and we told one of our clients, next week you're going to be in a deficit of $5,000, and they didn't think that was true, right? They thought this is definitely not correct based on the balances I'm looking at today. They would probably have a freak out, and they would call into RBC and they wouldn't be very happy with that user experience, right? And so we have to be very mindful of the context in which the end user is consuming this. Is it something that's going to drive a really emotional response? If that's true, we may have to build a little bit more controls around our machine learning system, or we may need to make sure that that model performs at a very high performance rating before we ever push it to production. Other things we need to consider about machine learning systems are expectations of generalization. And so let's use the example of a chatbot. So say we have deployed a chatbot that's built on top of machine learning. Now, all of us have used Google for many, many years. We have this expectation when we type into a search bar, right, that we can type it in any format. It doesn't have to be structured well, it doesn't have to be grammatically correct. Somehow Google figures out exactly what we want and seems to give us the information we need. Now, a lot of users will expect that same level of experience from our chatbot, right? That they can kind of engage however they see fit. And if that's not true, if our chatbot is not able to take in that type of information, we probably have to build some things around that to control that user experience a little bit more. And so these are the types of questions we ask ourselves during the design requirements phase. Now onto model development. And this is really where I want to spend a little bit of time, because it is the longest portion of our product development lifecycle. And it is obviously the thing that makes or breaks our product in the end of the day. And so this is really about developing that candidate solution, coming up with that model that meets all of our business and technical requirements. And one of the biggest challenges our product managers face through this phase of the life cycle is really how to keep things moving in the face of uncertainty. And this somewhat relates to the next point about nonlinear progress. Oftentimes what we'll find with machine learning, and this is particularly true in the research context, which of course we work in at Borealis, is we may go a couple of weeks where we're running all the right experiments, we're doing all the right things, but as it pertains to the performance requirements we have, we're really not moving the needle at all. And then what we'll find is all of a sudden, we'll run something, we'll make a small tweak to the model, and then we far surpass the benchmarks. And so we have this really, really nonlinear progress. So it makes it really challenging to call the project to say enough is enough. It might not make sense for us to pursue this, or to keep pushing just a little bit longer. And what we do at Borealis to manage some of this is make sure that we are managing with specific enough tasks, but also being flexible. And so while we use kind of an agile framework, we do build in some flexibility to that. And so we don't necessarily work off of two-week sprints, for example. Another thing that's really important is communicating nonlinear progress. And it can be really challenging to do this. And how we combat this is having really transparent and consistent communication. And this is both internally across our technical teams, but also with our business stakeholder. So they fully understand where we are and what they should expect in the next time steps. Another big place that we have to spend a lot of attention is, of course, determining or spotting these mismatches between technical and business value. And I'll use some examples to help explain what I mean by this. Let's use two different contexts. So in one context, we're building a recommender system. In the other context, we're building out a trading algorithm that's going to trade money within capital markets. So in the trading example, that technical performance, that accuracy directly relates to P&L, right? It is going to drive and determine whatever profit our trading algorithm makes. And so what that means as a product manager is we may consider pushing the team a little bit harder to get to a slightly better model before we put it into production, because that directly aligns with business value. Now, if we come back to that idea of a recommender system, there's likely a performance metric, a level of accuracy that will hit, where once we hit that, we basically plateau in terms of what business value that's driving back, the user experience that we drive there. And so as a product manager, you really have to think about when to call it, when is good enough, or when is the model that you have good enough, and when should you really push forward into the next phase of production. And it's not always all that easy to make that determination. You really want to make sure that you don't let perfection get in the way of driving value within the business, though. And last but not least, one of the things that I wanted to mention here was this idea of verifying experimental results. Remember that machine learning systems are stochastic and they learn based off of historical data. And what that means is in production, if they see data that is outside of the input space that we provided them and all of the training that we've done, the model may behave in a very strange way. And to make sure that we're managing that risk, what we do up front is we do a ton of experimentation, generally across many different time horizons and across different types of periods. So it could be on different subsets of a population. It could be within different market regimes, to have confidence that our model generalizes well across all the different types of input data that it may see once it's live. And that, of course, brings me to production. And a lot of the things that you think about in production are the exact same things that all of you guys would already know about. So not going to go too much into detail there. The key message I want you to leave with, though, on this one is we start thinking about these things very, very early on. So basically in discovery, we bring on an engineer to go through that entire life cycle with us. Of course, the engineering team helps with some of the model development as well, but we're really trying to map out the feasibility early on. Actually, about 95, or I should say 85% of machine learning projects fail when it's time to go to production. And it's because a lot of the technical constraints are not considered up front. Do you need access to GPUs? Do you have particular sets of data in prod data so that we can access them in production, et cetera? And there's all of these things that, no matter how good your model is, can basically kill the project right there. And so we think about these very, very early on to make sure that we're avoiding some of those risks. Another thing I want to highlight is the fact that there's this big shift within machine learning teams from DevOps to MLOps. You can think of MLOps as DevOps kind of on steroids. And this really relates to the fact that, again, machine learning models are stochastic. There is some variability in terms of how they're going to perform over time. And so we have to consider things like performance monitoring, model updates, model serving, model training, CI/CD, et cetera. And last but not least, support and maintenance. And the key thing here is really, once it's shipped in the world of machine learning, it definitely does not mean it's over. Things we have to think about here, of course, are monitoring, and that's in a couple of different contexts. Of course, we have to think about distributions of our data, both input and output. We have to think about performance monitoring in terms of our model performance. Of course, we also have to think of our product performance. And we should have predefined thresholds of what we expect during that time. We should also understand what we are optimizing for ultimately. Are we optimizing for product performance? So if latency requirements really matter, that might be the thing that we flag before model performance, for example. And last but not least, planning for what next. And this is a big one. So oftentimes when we put machine learning systems into production, one of the key outputs of that for us is actually the ability to collect new data so that we can continue to iterate on the model, or we can continue building new functionality and capabilities that we can deploy later. And so we're always thinking about not just getting this model into production, but really what comes next and how we can take full advantage of that production solution to build out the rest of our roadmap. And so quickly to summarize, I think the biggest thing is think end to end when you're building machine learning as a product manager. say double and triple check that machine learning is in fact the right solution. Please do not get caught in the dilemma of doing machine learning for machine learning's sake. Get used to experimentation and iteration. Constant transparent communication is definitely key. Switching from a DevOps to an MLOps mindset. And lastly, once you ship, that's definitely not the end of the story for a product manager when it comes to machine learning products. And so with that, I think we're going to pass it over to the Q&A section. We do have a bunch of resources on this actually on our website. So if you are interested in learning more, I do encourage you to go there and check them out. We also have a bunch of technical resources, both on the engineering side and on the modeling side. And so if you want to learn more about machine learning in general, I do encourage you to check those resources out.
Thank you so much, Alex. We have one question from the audience, and I would encourage the audience to add more questions in the Q&A channel or add to the chat channel. So our first question is from Ty. How do you determine maintenance pricing on an applied ML solution that might require further work in the future when it needs to be retrained or begins to experience performance degradation? And as a follow-up, is that already built into a usual product pricing or for maintenance?
Yeah, that's a really good question. And I have to say that at Borealis, we don't have to deal with too much of that in terms of selling our products and kind of pricing that into products that we sell because we are part of RBC and we build for RBC. And so I just want to throw that out there before I answer the question from our perspective. And what we tend to do is we will work with our business partners in laying out exactly what we think the retraining cadence should be. And of course, we don't know fully, right? If the market regime changed tomorrow, that could mean that we have to pull our model. But we try to have contingency plans in place for everything, SLAs, SLOs, all of those good things in place before we go to production. And as part of that, also thinking about what it takes to retrain and when we might want to come back to do model development. And of course, as part of that, what we'll do is experimentation. And so we have a really good sense of what does it take to retrain a model? How many GPUs for how many weeks will it take us? And some of our models take many GPUs for many weeks to retrain. And so that is actually a sizable cost. And all of that is kind of mapped out carefully. That being said, there is always risk when you deploy a machine learning model. I think that is a key thing to remember. And so you don't know what is going to happen. There may be some unforeseen costs in terms of you having to go back to the table and redevelop that model before you expected to. It's definitely one of the challenges I think we face, and is also one of the things that for us, we have to be really upfront with our business partners on. I think people don't realize all of these back-end post-production costs that you don't necessarily really need to consider with traditional software.
Awesome. So our next question is from Yusuf. How do you source your data when testing out your algorithms? Do you usually ask for a subset of production data and remove private information, or do you create mock data?
It's a great question, difficult to answer. It looks different in different places for us. We obviously work with various different lines of business that all have different types of data. And so one thing I will say is generally what we'll do is we'll sit with our business partners, figure out what is appropriate data to start considering. We'll get snapshots of that, run those baselines. And so generally we don't have the full data set when we're first starting. And then if things are looking good, we'll move on to getting out larger data sets. And in some cases for us, it's actually many terabytes of data that we're talking about that we do experimentation on. Before we go to production, regardless if we're using dev data for experimentation, we do a ton of testing. We basically have to rerun all of our experiments to re-verify that we're going to get that same result with production level data. In some cases, we actually do have access to production data for our research, but that is not common practice. I would say particularly in large enterprises, we're kind of a special case there. And so it really does depend. But in the end of the day, we go through a very long period of testing on all sorts of different fronts before we ever drive to production. And part of that, of course, is looking at those data pipelines, setting them up, and doing a lot of model testing before we would release that machine learning algorithm live.
Awesome. We have a question from Batter, who thanks you for the informative talk, by the way. And they're asking that if you could share an experience or example of a product that your team thought needed machine learning, but found out down the line that actually doesn't need one? And when did you find that out? Like, was it early in the dev process or was it later on? And what made you realize that?
Yeah, so that's a good question. I'm trying to think about an example of this that translates well to this question. So we actually have, I would say, gone through discovery work on several, but generally one of the big things that is a red flag for us is, of course, availability of data and our ability to translate that business concept into a machine learning problem. One area, though, that we're actually currently working on, and we're trying to find a reasonable solution to our business partner. I would say more often than not, what we end up finding is it's not so much about a question of whether it's a machine learning problem, it's whether we're ready for that solution. And so I'll give you an example that we're actually working through right now. We are looking at basically trying to help our clients better manage their money, right? And obviously this is one of the big focuses of RBC. And in order to do that, I think it's really important that we understand where our clients are with their money, right? So certain clients have a ton of surplus, other clients have a lot of debt. And generally some indicators of people that end up defaulting farther down the road would be things like falling into something we call revolver status. So revolver status is basically if you hold a balance for a lengthy period of time on your credit card and you're unable to make payments against that. And that is a really good indicator that at some future point in time, you're actually going to default either on that credit product or on some other credit product that you have. And so obviously, if we can flag that early on, we may be able to get in front of that and help those clients manage their money a little bit more effectively. And so we built out a machine learning solution for this. Basically, we built out a model that is able to predict revolver status. And one of the challenges that we're facing right now is really coming back to the table and saying, does it really make sense to use that complex of a solution for this problem? We probably have a ton of other flags and a ton of other information about a client already. Doesn't really warrant machine learning. We can do it, sure. And actually we've done it, right? We've built this great model. But now the real question comes back to the table of like, should we actually put this in production? Is this a different type of conversation we need to be having with the business partner? But oftentimes when we go forward through kind of discovery into feasibility and trying to, figure out whether something is machine learning, it's pretty apparent, pretty clear, pretty early on. It like basically as soon as we get our hands on data. And I should say that part of what we're able to funnel out up front is because we have a staff that are experts in machine learning, and so we can whittle out the things that aren't machine learning problems pretty quickly without having big conversations on them.
Right. Yeah, it's that was one of the questions that I had actually was when you have a problem that you're trying to solve, when do you decide that this is like we should apply machine learning versus taking the usual route, right? Like what is the delta in terms of benefit that applying machine learning will provide, right?
Yeah, and I think in that context, you really have to basically go back to basics and do cost benefit analysis, right? Like keeping in mind that machine learning is complex. There are all sorts of costs that come along with it. You really want to make sure that you're driving business value with that. Otherwise, if you can capture 95% of it with a rules-based approach, you're probably better off doing that, honestly. And I say that as someone who does this as a job, right? Machine learning is definitely not always the solution. And I think it's really a business question, right? Like you can make a lot of things into machine learning problems. The question you should be asking yourself as a product manager, though, is should I be doing this?
Right.
Is this the best solution?
Yeah. We have a question from Ty. Do you ever run into issues where you thought a particular performance benchmark would be sufficient? For example, about 90% accuracy, but then it turns out that it wasn't so good. It wasn't good enough for the use case ROI. How do you handle these situations in terms of reevaluating the project's potential?
Yeah, it's a really good question. And I have to say, we have been very lucky that this has never happened to the extent that we've ended up killing something, right? So we're lucky in that. But yes, I think this situation has happened to us a number of different times in a number of different contexts. And I'll come back to something that I mentioned in the talk is one of the challenges that we really face is Sometimes it's very difficult to translate business value to technical constraints or technical thresholds. And often that is a process. Usually when we start off with a particular metric that we're working towards, we find out after a lot of conversation and a lot of experimentation that maybe that's not sufficient to define what we really need as a product. And so it's really about iteration. What we do for this actually is just run a ton of baselines, do that translation, and constantly bring them back. I mean, the amount of experiments that our team does is pretty darn insane. And that GPU cluster that I talked about, we often utilize that 100%. And like, that is a lot of compute. We're very, very lucky that we have access to that, but we just run experiment after experiment and try to distill that down to business, bring it back and iterate. And so that happens to us. I would say almost on every project, to be honest. It's a constant thing that we have to be on top of. Luckily, again, like I said, we've never gotten to the point where we thought we really had a candidate model and we were about to push to production and had to pull back. And so that's nice. But yeah, it's a challenging conversation for sure.
Right. We have a question from Nikhil, who's asking whether you could share some more examples of AI projects versus machine learning projects that you have worked on, your team's worked on.
Yeah, sure. So I can share some examples of various different types of machine learning that we've deployed. Unfortunately, I can't talk about all of the great work that we do. We're not allowed to talk about a lot of it publicly, which is always a shame when I do these talks. But there are a couple of things that I am allowed to talk about. One is one I leaned on a little bit in my presentation, which is around cash flow forecasting. So we have very recently launched through Nomi Forecast on the RBC mobile app, cash flow forecasting capability. That is basically client specific. So it's based off of your own historical data, and it will provide you a view out 7 days on what payments are going to be coming up. And we're going to be expanding out functionality over this next year. And so that is a pretty straightforward forecasting problem with machine learning. And we've used a couple of different approaches. We're actually now modifying that model a little bit to have a little bit more functionality and flexibility in terms of how confident we are with those types of forecasts and when we should actually be showing a forecast versus holding it back. So that's one example I can talk about. Another one, which is really exciting and got a lot of press for us, was something we call Aiden. Aiden is something we built for capital markets. Aiden uses reinforcement learning algorithm. So it's a deep learning model. And basically what it's able to do, it's a block trading system. So basically institutional clients, let's say Ontario teachers, will come to RBC and say, I want to offload this giant chunk of equities. And of course, if we did that, we threw those all into the market all at once, what you would find is that would actually move the price, right? And Ontario teachers wouldn't be in a great spot. They'd lose a ton of money. And so what these institutional clients do instead is basically chunk those up into smaller blocks, and over time, they will release them into the market. And what Aiden does basically is helps us optimize. And it takes in live market data, and it updates its state of understanding of the world. And based off of that state of understanding, it will optimize either to make a trade or not to make a trade, how much it should trade, when it should trade. And this was a pretty massive technical feat for us. For context, reinforcement learning has really largely lived within the gaming industry. So, if you have computers that play chess, or there was actually a documentary on Netflix called AlphaGo, and it's always kind of sat in that context. We brought it into this real world context of trading, obviously, where there's real money to lose. So there's a lot of risk around that. And we found there was a couple of periods throughout COVID where the markets were a little bit crazy. They were quite volatile, and we were able to leave Aiden live. It basically updated its understanding of the world and was able to continue optimizing those trades for institutional clients, maintained its performance throughout. And it's like a huge technical feat. We were very, very excited when we heard from capital markets that they left it on. So it was a big one for us.
If I could add to that topic there with COVID, right? Like it happens, like it's a once in a lifetime thing. It really disrupts patterns. And so when you have a machine learning model in production, especially like the work that you did around kind of personal finance, cash flow prediction and such, right?
Yeah.
And when something disruptive as this happens, as a product manager, like what what do you do? Like, what do you monitor? Do you take things out of production? Do you stop things, or do you actively monitor? What do you do in that case?
It's a really good question, and it's a big challenge I think we have to face. And there's a couple of different tools I think we have in our toolkit to help deal with this. One is what I mentioned in my talk around experimentation. So one of the things that we would do with the cash flow forecasting model, for example, is we wouldn't only train and test on this last year. We're going to build out an algorithm, and we're going to make sure that we've tested it over many, many, many years of data. And you're not looking to optimize on a particular data set, right? What we're trying to find is that model that is going to generalize most effectively across all of those different periods of times. And of course, this builds our confidence that when it starts to see new inputs or changes in inputs, it will have seen something maybe similar to that and won't do anything totally ridiculous, right? And so one thing we have to do up front is experimentation. And then when it comes to production, there's a couple of different things that we have to think about. One is oftentimes with machine learning systems, we build controls around them. This is definitely true in places like capital markets and risk management, where we wouldn't just build an algorithm, a trading algorithm, and like release it into the wild, right? There would be risk controls built around that to say, if this algorithm starts to have too much exposure here, we're gonna pull it. And you know, we can't just release it into the wild. And there's actually been some really interesting cases. If you want to learn a little bit more, Knights Capital, for example, is a hedge fund that lost like hundreds of billions of dollars within a half an hour based on an algorithm. And there was basically a bug in the code and had no controls around it, was obviously incredibly detrimental. Not what you want. So one is building controls, really thinking about all of those edge cases. The second obviously relates to monitoring. And there's many different things that we have to think about when we're thinking about monitoring for machine learning systems. One is, of course, data distributions. So if we see our input distributions changing materially, we may want to pull the model. If we see our output distributions changing materially, may be an indicator that we want to pull the model or, you know, do a deeper investigation. We have a series of performance metrics that, of course, we would determine upfront to make sure that we are performing stably over time. For us, it's not necessarily one day. We could see a little tick down as long as we have stable performance over time. And then, of course, there are all of the other things that you would normally monitor for engineering systems like latency, et cetera. But there's a lot more considerations on the monitoring front. One thing, though, we do have to remember, and this really comes back to the beginning in discovery and feasibility, is if the only data set that you have is data that may not be representative over time, you may want to wait. And we've actually had conversations with certain stakeholders where the only data available has basically been during COVID. And that's probably not going to last going forward, right? We don't know, it may, but it may be a waste of our time to develop a model if that's all we have access to, knowing how different the last couple of years have been compared to, you know, all of history.
Right. We have a question from Ty. How do you estimate the ROI of a particular ML solution candidate? Do you ever use A/B testing to be able to show the actual gain from using ML versus a simpler rules approach?
Yeah, that's a really great question. And I would say there's varying levels of complexity in answering that question. In some cases, it's very straightforward. So again, capital markets case, we can directly see if we're going to build out an algorithm for trading, you know, how much higher that P&L is versus a baseline solution. But it really helps us to have some form of baseline and to see how much better we can perform over that. It's very similar in risk management. Oftentimes what we're doing is improving upon models that already exist. And so we can directly kind of see how much the lift is and translate that into dollar value. In some cases, though, it is a little bit more challenging. We definitely do lean on things like A/B testing to verify over time that we are actually getting the lift that we expect. In some cases, we can see that quite quickly. So within a series of months, we can know whether our mobile app users are engaging well with our product, we're getting good feedback on it. There are other cases, though, where it takes a really long time to figure out whether your model is actually performing well. Really great example of this would be credit adjudication, right? So on average, people, it takes them about, depending on the product, 5 to 7 years to default on a credit product. If we put in a machine learning model today, we might not find out for many years whether that performance actually provided the lift that we are estimating. We do lean on things like simulations, though, a lot. We have these for market simulations, for example, where we'll do testing and we can infer what our performance will be. There's also very similar things that we use when it comes to our retail clients as well.
Right. And as a product manager who's now building ML-based products, or has a product but is thinking of leveraging ML-based solutions for it, right? How much does a product manager actually need to know the inner workings of the model? Like a typical software, yes, you would know the detailed requirements and all that, but for something like this, like what is the level of technical knowledge they would need to have?
It's a really good question, and I think it's difficult to answer, to be honest, because I think there's a spectrum. It really depends on what task you're trying to do and how complex that system needs to be to get business lift. There are definitely a lot of opportunities within banking that you probably could take a fairly, straightforward XGBoost, Python package off the shelf, apply it to your data set, and get some meaningful lift. And I would say in that context, obviously you want to understand what the model does, what the risks and limitations of that model are, and any considerations that you may have to make in terms of the things that we talked about already in managing risk once it's in production. That being said, if you're looking at building out sophisticated machine learning models that have multiple objective functions that use lots of complex data, you probably want to get a little bit deeper into things. And so a lot of our product managers, I shouldn't say a lot of, all of our product managers at Borealis have a pretty deep understanding of machine learning, not to the point that they know how to code anything or know all of the nitty-gritty details of how that model works, I should say. But they definitely are very well versed in algorithms, as well as, I would say, on the engineering front, all of the other considerations that we have to make there as well. And so if you're interested in this space, there's a lot of great articles that have come out recently around ML ops, for example, and how that looks different from traditional DevOps and some of the things that a product manager needs to take into consideration. But I would say for us specifically, all of our product managers are quite heavily technical.
Right. Thanks for that. And we have one more question from Adesh. How do you control the adverse effects of an underfitted model on user emotions while working with prescriptive analytics?
Yeah, so if I understand the question correctly, it's basically, if we haven't built a great model and it has some adverse effects on our end user, how do we control for that? And I would say it's largely a lot of the tools that we've used are fairly similar to traditional product management, right? We go out and we do surveys, we do user groups, we'll build wireframes, and really understand what types of emotional responses we're going to get from various different things that we could show them. And some of it comes down to just the way that it's presented or the language we use around that, making sure that people understand that this is a forecast. It's not fact. And of course, that is not my area of expertise in terms of picking all of the perfect words to put around that, but we do a lot of work with user groups to make sure that we've thought about some of those sensitive areas. One of the things that we really have to think about as well is people's emotional response to knowing something has been decided by a machine. And obviously this ties into a much larger concept of kind of the ethics of AI, the black boxiness of AI. Probably could have a whole hour-long conversation on all of those pieces. But we also have to make sure that we're transparent with our clients, but doing it in a way that it's not going to kind of get their backs up, right?
Right. Well, we're almost at time here. Thank you so much, Alex. I think there was a very interesting discussion, and I think we work on so many products now that leverage machine learning. I'm sure the audience found it really valuable as well. So thank you so much for making the time to present this to us. A really valuable discussion. And thank you, audience, for joining us today as well, taking time out of your busy schedule to attend the session. I hope you enjoyed it. Keep an eye out for events from the Toronto chapter. Our next session will be on November 10th, and we will have Scott Affleck joining us, who's former VP of Product for RateHub, and he will be talking about products that are built for online experiences, but for offline experiences as well, such as the sales channel. So that'll be an interesting session as well. I'll pass it over to Ryan.
Thank you, Arun, and thank you, Alex, for a great talk. Thank you to everybody who tuned in. And just a heads up to let you know, this webinar will be featured on our website next week. So if you are not already subscribed to our newsletter, please do so that you get notified about that. And with that, I'll wish all of you a good afternoon, good evening, wherever you are. So have a great day. Thanks, everyone.
Thank you.